Some planets are so strange, they don't follow our rules. They make our physics seem like suggestions, just local guidelines. We're going to look at 20 of these alien worlds. Places where reality gets rewritten. You have planets with diamond hearts, skies that rain iron. By the end, you'll see the universe differently, not just rocks and gas. It's a laboratory, a place for the impossible. How does a world become darker than coal? How does a year pass in just 18 hours? Every discovery we'll see is a challenge. A direct challenge to how we understand nature. And when the cosmos does this, when it regularly defies our best explanations, what does that mean? 55 Cancri E. Its surface is a vision of hell, a world bathed in the scorching light of a star so close, its entire year is just 18 hours. The heat is so extreme, rock melts into glowing seas. But the real story isn't on the surface. It's buried deep, under pressures that would crush our strongest materials into something alien. This world is profoundly rich in carbon. The same element in the pencil on your desk, but here, under these impossible conditions, that carbon is forced to become something else, something precious. Scientists believe the crushing weight of this super-Earth has crystallized a staggering part of its interior into a structure of diamond, so imagine a geological heart. Not of molten iron like Earth's, but of solid, glittering gemstone, and this isn't just a curious detail. It rewrites the first chapter of planetary geology. We always assumed rocky worlds would be like ours, built from silicates and oxygen, but 55 Cancri E is a defiant counterexample, a carbon world, where the rules of chemistry play out on a scale of pure extravagance, and it forces a simple question. If one world can be forged from diamond, what other impossible treasures are waiting in the dark? Locked inside planets we haven't even found yet. A world can be made from treasure and another from shadow. There's TRAPPIST-2b. It's a gas giant, orbiting so close its year is just 2.5 days. Temperatures go over 1,000 degrees. You'd think a world like that would glow like an ember, reflecting its star's light, but it doesn't. It does the opposite. TRAPPIST-2b is the darkest planet we know. It's a void. It reflects less than 1% of the light it gets. Blacker than coal, blacker than paint. And this isn't the dark of some cold, distant rock. This is a world bathed in stellar fury. Our models for hot Jupiters predicted bright clouds, reflective clouds, maybe sodium or potassium, bouncing light back. TRAPPIST-2b laughs at that. Its atmosphere is a phantom, it eats light, so scientists have to guess. What's the chemistry? Could it be vaporized titanium oxide? Something that absorbs visible light with terrifying efficiency. Or gaseous sodium, behaving in ways we've never seen. Whatever the mix, the result is a near-perfect absorber. It drinks its star's light. Heated to an incredible degree, it re-radiates that energy. Not as a bright reflection, as a faint, deep red glow, a ghostly ember in a perpetual noon. That blackness forces a realization. We've only just started cataloging the palette of the cosmos. We thought we knew the basic colors of planets. TRAPPIST-2b says we were wrong. Its existence is a direct challenge. It pushes us to write new chapters of atmospheric physics. For worlds where daylight doesn't mean brightness, it means a deeper shade of night. And if a planet can defy us so completely with its color, what other sensory impossibilities are waiting? What happens when a world doesn't just absorb light, but twists weather itself into something unrecognizable? That deep blue color. It looks like an ocean world from a distance. Astronomers saw that blue by watching starlight pass through its atmosphere, but it's not water, it's not calm. It's the color of a furnace. The blue comes from a sideways rain. A sandblasting of molten glass. The weather there is a form of homicide. Winds move at 5,400 miles per hour. That's nearly 7 times the speed of sound. For comparison, a tornado on Earth might reach 300. This planet's entire climate has the force of a continuous shock wave. It's a fundamental sculpting force. The planet is tidally locked. One side always faces the star broiling. The other side is eternal night. That difference should create a staggering temperature contrast. But these supersonic winds act like a planetary mixer. They transfer that blistering heat from the day side to the night side with terrifying efficiency. The mechanism is brutal. The extreme heat vaporizes silicates, the stuff of sand and rock, turns it into the atmosphere. The winds pick up these particles and hurl them around the globe at ballistic speeds. So you're not looking at rain clouds, you're looking at a global storm of microscopic molten glass, a horizontal inferno scouring every inch. This environment exists in a regime of physics we don't have here. Our fluid dynamics models, built for Earth and even Jupiter, strain to explain how such velocities are sustained. What drives it? It's the raw, chaotic energy of a star. Pumping heat into an atmosphere with no calm refuge, a feedback loop of unimaginable power. HD 189,733b shows that a planet's climate can be more than weather. It can be a single planet-enveloping cataclysm, a permanent state of elemental fury, and if wind alone can redefine a world so completely, it makes you wonder. What happens when the planet itself isn't a sphere but a shape that shouldn't even exist? Proxima b orbits Proxima Centauri, our nearest star. It's a red dwarf, faint. And the planet is in the habitable zone, where water could be liquid, but it's not like Earth. It's tidally locked. One side always faces the star, the other side faces space. So you have a day side under constant light. It could be scorching, and a night side in permanent shadow. Temperatures there could drop near absolute zero. Between them, a thin band of twilight, where day meets night. The physics are a puzzle. How does heat move? If the atmosphere freezes on the dark side, the whole world could become an ice ball. Our models struggle. They often need a thick carbon dioxide atmosphere to insulate it, or maybe heat from underground from a restless core. Without that, the air could collapse into ice on the dark side. There's a possibility called an eyeball planet, a single ocean of liquid water, right under the star at the center of the day side, a blue eye staring into space. And around it, a global desert of rock and ice. So habitable isn't a global condition. It's local, fragile. Life would be trapped in that narrow twilight band. A sliver where temperatures might be right, a ribbon between burning day and frozen night. It makes you ask what habitable even means. Is it a planet or just a region on a planet? Proxima b is many things at once, a boiling desert, a frozen waste, and a temperate band, all on one sphere. And if one planet can have these fractured identities, what about a world that isn't one but two? WASP 76b, a planet where the forecast is always molten iron rain. It's an ultra-hot Jupiter orbiting incredibly close to its star. The day side is a crucible. Temperatures there go beyond 4,400 degrees Fahrenheit. That's hot enough to vaporize iron. The metal doesn't just melt, it boils away, becomes a metallic vapor in the superheated atmosphere. But that's only half of it. The planet is tidally locked. One face is eternal day, the other eternal night. The temperature difference between them is staggering, thousands of degrees. That drives supersonic winds that race from the day side to the night side. And as this metallic vapor gets carried into the cooler darkness, something impossible happens. The iron condenses. It goes from a gas directly into liquid droplets, and then it falls. So the sky on the night side of WASP 76b, it perpetually weeps molten metal. It's a phase of matter, a weather cycle we just don't have on Earth. Our water cycle, with evaporation and condensation, is gentle by comparison. Here, it's replicated with a brutal, elemental ferocity, using a material we think of as solid and heavy. The existence of this iron rain means a complete rewrite of atmospheric science for these extreme worlds. Metallicity isn't just a footnote in their composition. It's the active ingredient of their climate. It dictates the chemistry of their clouds, the very nature of their storms, and that raises a puzzle. How does an atmosphere survive that stellar fury at all? Why isn't the entire gaseous envelope of the planet just boiled off into space? The answer has to be a delicate, violent balance. The star's gravity and the planet's own immense gravity, they likely hold the atmosphere in a tense embrace, even as its upper layers are continuously stripped away. WASP-76b is a laboratory for material science under duress. It shows that under enough heat and pressure, the familiar rules of substances break down. Iron behaves like water. The sky becomes a refinery, and if a world can turn metal into weather, what other alchemies are waiting? What happens when a planet isn't just hot, but so inflated and light it defies the very concept of density? The density of cork, that's the thing with HTP-1b. It's a gas giant, hydrogen and helium, but it floats in our models. It's so light for its size. It's puffed up for its mass, it's enormous, it's inflated, and that breaks a rule, a basic rule we had. Giant planets form hot, they form from gas and dust collapsing. And then, over time, they should cool, and as they cool, they contract, they get smaller, denser. Jupiter did that, Saturn did that, but HTP-1b didn't. It hasn't contracted, it's stayed inflated, it's bloated against its own gravity, so something's keeping it puffed up, something inside is fighting that squeeze. Pushing out, and scientists, they're looking at the clues. One idea is tidal heating. Maybe the orbit isn't a perfect circle. The star's gravity tugs on it, stretches it, squeezes it as it goes around. Like kneading dough, that friction inside, it makes heat. Immense heat, and that heat pumps energy into the atmosphere, keeps it expanded. Another clue is the atmosphere itself. Its composition, it might be unusual. Certain elements could act like a blanket, a very efficient thermal blanket. They trap the star's heat so well the interior can't cool down. It can't start the contraction, so it's stuck in this expanded state, this permanent youth. And this isn't just a curiosity. It challenges our models. Our timelines. You can't just look at a gas giant's mass and know its size anymore. Its history matters. Its relationship with its star matters. The chemistry of its air. They all write a different story. HTP-1b tells us planetary middle age isn't a given. Some worlds, through orbital dynamics or atmospheric chemistry, they keep their birth heat. They defy the settling, the slow cooling of time, and if a planet's size can lie about its age, about its internal fire, then what happens when we find a world somewhere it shouldn't be at all? A planet in a place so hostile, its existence seems like an error. Kepler 16b, it's a real place, the first planet we ever confirmed that orbits two stars. Saturn-sized, you could imagine standing on one of its moons, maybe, and watching two suns go down. That's Tatooine, but it's not fiction anymore. The physics of it, though, that's the real marvel. Our whole idea of how planets form, it was built for quiet systems. A single star, a binary system is a battlefield. Two stars in their own dance, pulling at the disk of dust and gas where planets are supposed to come together. That chaos should tear everything apart. The gravity should keep the material from ever clumping into a world. But Kepler 16b is there. It found a stable path. It orbits far out, circling both stars at once. Its year is about 229 days, a loop around the binary heart of its system. That orbit is in what we could call a gravitational habitable zone, where liquid water could exist, though the planet itself is a gas giant, probably cold. Just the fact it's there, stable, it rewrites the first chapter of planetary science. It proves planets can form in profound chaos. that the cosmic real estate for new worlds is so much bigger than we thought, but stability is only half of it. Think about the climate on a moon there. The light would never be constant. The two stars eclipse each other. The total radiation hitting the planet would pulse and fade in a complex rhythm. Days would vary wildly in length, in brightness. The heating patterns would be intricate, unpredictable by any earthly standard. Seasons, if they existed, wouldn't come from a tilt. They'd come from the shifting balance of light from two different suns. It's a climate modeler's ultimate puzzle, a world of permanent celestial choreography. Kepler 16b opened the door. Since then, we've found many more circumbinary planets. Some systems have multiple worlds dancing around twin stars. Each one is a testament, nature finding order within apparent chaos. It shows that peace for a planet isn't about solitude. It can be about finding the perfect rhythm within a gravitational symphony. And if a world can find harmony between two suns, what happens when the entire system isn't just a dance, but a relic from another galaxy entirely? A world can lose its sky and still find a way to breathe. GJ 1132b is a super-Earth, a rocky planet about the size of our own, but it's in a furnace. It orbits its dim red dwarf star so close that a year there is just 1.5 Earth days. That closeness should be a death sentence for an atmosphere. For billions of years, the star's radiation and stellar winds should have stripped away any original blanket of hydrogen and helium. Leaving behind a barren rock, the physics seemed clear and unforgiving, but when astronomers looked, they saw the signature of an atmosphere. It was still there. A beautiful defiance. How does a world keep its sky when the rules say it should be naked to space? The answer is, it's not wearing its original coat. It has woven a new one. This is likely a secondary atmosphere created from within. The immense tidal forces from its star, constantly squeezing the planet's interior, could be driving relentless volcanic activity. The planet's molten heart may be outgassing, venting new gases like carbon dioxide or methane from its crust. Or maybe colossal impacts dredge up volatile materials from deep below. It's a form of planetary respiration, a world literally exhaling a new sky from its own geologic lungs. This blurs a line we thought was firm. On Earth, geology and climatology are separate sciences. Here they are the same story. The planet's internal heat directly dictates the composition of its air. Its climate is forged in fire. This resilience rewrites the final chapter for close-in worlds. We thought atmospheric loss was a one-way trip to eternal silence. GJ 1132b argues it can be a cycle, death and rebirth. It suggests some planets, through sheer tectonic will, can reinvent themselves against cosmic odds. Their story isn't written solely by their star. It's also written by the simmering activity within. If a world can regenerate its own protective shroud, it makes you wonder what other forms of planetary tenacity are waiting in the data. What happens when a planet doesn't just renew its air, but is itself a fragment of a much older, impossible structure? GJ 436b is vanishing. It's a Neptune-sized planet, an ice giant, but it's so close to its star. The radiation is intense. It heats the upper atmosphere until gravity can't hold on. Hydrogen atoms boil off. They escape into space at a staggering rate. But they don't just drift away. The star's wind catches them. It sculpts the gas into a vast tail, comet-like, stretching over 10 million miles. From a distance, the planet isn't just a sphere. It's a sphere with a streaming veil, a brilliant veil, a beacon of its own dissolution. This is planetary evaporation, but on a scale we can actually see. The physics are a brutal tug of war. The planet's gravity tries to keep its envelope intact. On the other side, the star's radiation and particle wind act like a cosmic sandblaster. For this planet, the star is winning. Atom by atom, the atmosphere is stripped away. That forces a revision. we classified worlds as gas giants, ice giants, rocky planets. We thought these were permanent states. GJ 436b shows they can be transitional. An ice giant over billions of years could be reduced to its barren core. A rocky core, a world transforming from one class into another right before our telescopes. Watching this is like seeing a cosmic hourglass. We're catching a planet in a fleeting phase. A phase that might last a mere billion years in a multi-billion-year lifetime. It gives us a dynamic view of planetary death. Static snapshots could never provide this. It's not an explosion, it's a slow, relentless sigh. A world exhaling itself into the void. The ultimate fate is a ghost, a dense, heavy core, all that remains of a once swollen giant, orbiting silently where its atmosphere used to glow. This changes the meaning of a planet's location. Orbit isn't just an address, it's a timer, a countdown to a fundamental metamorphosis. And if a world can evaporate into a brilliant tale, what other transformations are possible? When a planet doesn't just lose its atmosphere but is forged from the ashes of a dead star, 16 hours, that's its whole year, a day here, and it's gone around its star 1.5 times. It's a hot Jupiter, just pure frenzy, but the speed isn't the unsettling part. It's that the dance is speeding up, the planet is spiraling inward, falling toward its star faster than we've ever seen outside our own system. We're watching a death spiral. This is observation, not theory. In just a few years of watching, they saw the orbit shorten. It's decaying, and that gives us something rare, a laboratory for gravity. We can test tidal forces on a colossal scale. The star's gravity pulls on the planet, creates friction inside it. That friction makes staggering heat. Could inflate the atmosphere, churn the interior with planet-wide forces, but that friction also breaks its orbital energy. It's a feedback loop. The closer it gets, the stronger the tides. The stronger the tides, the more energy it loses. The more energy lost, the closer it falls. This world defies the idea of clockwork orbits, of serene, eternal ellipses. It shows a gravitational relationship that's dynamic, violent, and transient. The question isn't if it will be consumed, but when. Estimates say it could be drawn into its star in a few million years. A cosmic blink, TOI 2109b, is a reminder that stability is often an illusion or a temporary truce. It shows gravity's raw power, not just to create orbits but to unravel them. Watching this is seeing planetary destiny written in real time, a lesson in celestial mechanics with the highest stakes. And if a giant planet can be devoured, it makes you look at the other end of the scale. What's left after? Could something even stranger be forged in that aftermath? At the center, it's just a whisper. WASP 107b is an ice giant. But it doesn't match what you'd expect from that. It's enormous in size, puffed out like cotton candy, but the mass at its core is shockingly small. Under the standard rules, this shouldn't be possible. The leading theory is core accretion. It says a giant planet starts with a massive, rocky core. At least 10 times Earth's mass. That core's gravity pulls in the hydrogen and helium. It builds the giant, but WASP 107b's core is far too lightweight. It couldn't have done that job. It's a tiny pebble trying to hold onto a mountain of fog. So how is this world here? Its existence challenges that model directly. Astronomers have to consider a different birth, more dramatic. Maybe it formed through disk instability. A dense clump in the protoplanetary disk collapses under its own gravity. Like a star forms, it skips the massive core stage entirely. Or maybe it did form farther out, with a more traditional structure, and then migrated inward. But that journey through the violent inner system should have ripped its fluffy envelope away. Yet here it is, orbiting perilously close to its star. A wisp of a world in a furnace. Its resilience is as puzzling as its origin. This cotton candy planet forces a humbling admission. We may have been telling only one version of the story. WASP-107b suggests the universe has multiple blueprints. Some worlds are built from the ground up, rock first. Others might condense whole from the chaos of the birth cloud. Its nature is paradoxical, a lightweight giant in a scorching orbit. It opens a new chapter. It asks what other impossible structures we've dismissed. Because they didn't fit the old narrative. If a planet can be both gossamer and enduring, what does that say about strength, about the strength hidden in apparent fragility? WASP-19b has a sky that would be solid here. Its atmosphere holds titanium oxide. That's the white pigment in our paints and sunscreens. But there, it's not a powder. It's a vapor, a gas superheated to thousands of degrees, swirling in a permanent twilight. And this vapor absorbs stellar radiation. It does it with a terrifying efficiency, trapping heat high up. That creates a thermal inversion, a complete reversal. On Earth, you go up a mountain, it gets colder. On this world, it gets hotter. The upper atmosphere is a blistering cap, warmer than the gas below. It's like a furnace in the sky with a slightly cooler room underneath. This one compound, this vaporized mineral, flips the entire logic for these planets. Our models built for places where heat sinks, they're useless here. The climate is inverted. The rules of heat flow are rewritten. Titanium oxide isn't just a curious ingredient. It's the master switch. It dictates where heat goes, how it moves, what the weather can become. This is a chemistry lab operating at a scale we can barely conceive. Processes that need a furnace and a vacuum happening naturally in the open sky. It forces a question. What other common earthly rocks and minerals are waiting out there? Could there be worlds with vaporized quartz clouds or aluminum oxide storms? WASP-19b suggests the periodic table doesn't just make planets. In the right crucible, it becomes the weather itself. And if a single element can redefine a global climate, what happens when a whole planet is built from the remnants of a stellar catastrophe, the TRAPPIST-1 System? 7 Earth-sized planets around a cool red dwarf. Their orbits aren't random, they're locked in a rhythm, a resonance. Their orbital periods are ratios of whole numbers. The innermost planet goes around 8 times, the second one does 5, the third does 3. It's a chain of synchronized orbits, and it's a delicate configuration. In a system that compact, with planets that close, gravity should have caused chaos by now. Collisions or ejection, but they're still there. A clockwork ballet that's lasted billions of years. This perfect harmony, it defies our simulations. The N-body models can't easily keep it stable. Its existence suggests a gentle history. These planets probably formed farther out. Then migrated inward together in lockstep, without the violent scattering we see in other systems. It was a calm, orchestrated drift. For us, it's a different kind of planetary story. One of cooperation, but this resonance has consequences, especially for TRAPPIST-1e. That's the planet in the habitable zone. The constant, rhythmic tugs from its 6 siblings, they don't just maintain the orbits. They squeeze the planet's interior. That's tidal heating, on a scale we don't see in our solar system. The result could be hyperactive geology, a crust constantly churned by its neighbors. That might fuel intense volcanism, a dynamic, ever-changing surface for life. It's a double-edged sword. The internal heat could power deep-sea vents. Potential cradles for biology, even under an ice shell. But it could also mean a surface that's too volatile, constant eruptions, a thin, toxic atmosphere. TRAPPIST-1e doesn't just orbit a star. It exists in a web of gravitational relationships. They shape its soul, its climate, its geology, its potential as a living world, all written by the music of its siblings. This system makes orbital dynamics tangible, a physical force. It asks how such perfect order emerges from the chaos of planetary birth, and it makes us listen. Not for radio signals, but for the silent, gravitational symphony. That might be the true song of a living system. The chemical signature of a planet should be stable. A fingerprint, but HD 209,458b, one of the first transiting worlds we found, gives us a surprise. Its atmosphere is dominated by carbon monoxide, and our models predicted a clear signal of water vapor. But there's a silence there, a telling absence. For a hot Jupiter like that, with its temperature and pressure, equilibrium chemistry says oxygen and hydrogen should bind. Water should be abundant. The lack of it is a direct contradiction, a mismatch between what we expected and what we see, so something reshuffled the elements. The answer seems to be motion, relentless motion. The planet's own atmospheric dynamics could be so violent, they're pulling material up from deep below. Global winds, like planetary conveyor belts, could be dragging carbon-rich gases from the interior up into the atmosphere we can observe. That would overwhelm the oxygen-rich chemistry we expect higher up. It means the winds are doing more than moving clouds. They're rewriting the planet's composition from the inside out. The atmosphere we see isn't a representative sample. It's a snapshot of a churning, vertical factory, so we have to revise how we read the cosmos. We can't look at a spectral line and assume it tells a simple story about global composition. That line is a message passed through a turbulent filter. It's shaped by currents we can't see, by mixing on a scale we can barely model. HD 209,458b asks a pivotal question. Can global winds forge a new chemical identity for a world? The evidence suggests they can, that the sky isn't a passive layer, it's an active, transforming engine. And if circulation can hide an ocean's worth of oxygen, what other elemental secrets are being concealed by the weather? Then you have to ask, what happens when we look at a planet that seems to have no weather at all? Because its very surface is a substance that defies the concept of solid ground. K2141b. It's a place where the geology is the weather, an ocean world, but the ocean isn't water. It's a global sea of molten rock, hundreds of miles deep under a permanent blazing sun. The planet is tidally locked. One side is a permanent furnace. The heat there is so intense it doesn't just melt rock, it vaporizes it. The surface boils. It sends plumes of mineral vapor, silicon, sodium monoxide, up into a thin, scorching atmosphere. That's the first step. The vapor gets caught in supersonic winds whipped around to the night side, a hemisphere of eternal, deep space cold. And there, in that profound freeze, the vapor condenses. Not into water droplets, into clouds of microscopic rock dust, and then it precipitates. The sky rains pebbles, tiny stones of solidified lava hailing down. But the surface on that side is the same lava ocean, now frozen solid into a crust of bedrock. So the pebbles fall, they accumulate, they're slowly dragged by the planet's rotation back toward the day side, where the crust melts again, rejoining the molten sea, ready to be vaporized. It's a complete global rock cycle, a lithosphere breathing itself into an atmosphere and back. On Earth, our water cycle is gentle. Evaporation, clouds, rain. Here, that same process is reenacted with the violence of a forge. The physics are alien. We have to study the phase changes of silicates at planetary scale, how a rock cloud forms, how a pebble storm behaves. There's no terrestrial analogy. It forces a shift in perspective. We can't think of planetary systems as being about one set of materials anymore. A planet is a set of processes, and those processes will use whatever materials are available. On an ice world, it's a methane cycle. On this world, it's a rock cycle. The weather report for K2141b is a forecast of stone, highs of 2,700 degrees, lows near absolute zero, winds at Mach speed, and a 100% chance of rocky precipitation. It's a world built from a single, relentless transformation. And if a planet's entire identity can be a phase change, what happens when we find a world that isn't transforming at all? one that's been frozen perfectly in its very first moments of life. LTT 9779b is a contradiction, a forbidden world. It's the size of Neptune, but it orbits so close to its star that its year is just 19 hours. Temperatures there reach 3,200 degrees. This area is called the Hot Neptune Desert, and that name fits. Our models for how planets form and move say a world like this, with this mass and makeup, shouldn't be there. It's an anomaly, like finding a glacier inside a volcano. The physics seem absolute. That close, the radiation and stellar wind are immense. Over millions of years, they should have stripped the planet's entire gaseous envelope away, blown it all into space, leaving just a bare, scorched core, a silent remnant. But when they looked, astronomers saw the clear signature of a thick, shimmering atmosphere. LTT 9779b still has its sky. It held on. That defiance is what makes it important. Its survival in that brutal place forces a rewrite. Our theories of atmospheric loss seemed solid, but now they have to explain this exception. How does a planet keep its atmosphere against those odds? The clues suggest two possibilities. The first is a shield. The planet might have a massive metallic core, one that creates a powerful, global magnetic field. A magnetic bubble extending out into space could deflect the star's constant particle wind. It could act as a force field, protecting the atmospheric gases from being stripped. The second possibility is about timing. Maybe this world is a recent arrival. It could have migrated inward from a cooler, safer orbit only in the last 100 million years. A cosmic blink. If that's true, we're seeing it in a fleeting state. We're witnessing the start of its end, a slow evaporation that's just begun. But even that idea has issues. Migration itself is violent. The journey through the inner system should have been disruptive enough to tear the atmosphere apart. So its presence intact is a puzzle on two levels. LTT 9779b is more than data. It's a challenge. It tells our models they're incomplete, that our understanding of how planets live and die in extreme places is still just a sketch. This world, persisting in its forbidden zone, asks us a question. Are we seeing a rare fluke, or is this the first of many, showing us planets have hidden defenses, ways to endure that we're only starting to understand? WASP-121b. It's a world where water doesn't bring life, it brings a puzzle. This is an ultra-hot Jupiter, a furnace, but its upper atmosphere holds water vapor. Something we know well, yet here that familiar molecule is in a place it shouldn't survive. The stratosphere, that's a high layer of the atmosphere. It's so scorching, temperatures exceed 3000 Kelvin. That's hot enough to tear water apart. Ultraviolet light from the star slams into these molecules. It breaks the bonds between hydrogen and oxygen. That process is called thermal dissociation. So you have a layer of the sky, a layer where water is constantly being created and destroyed. A churning zone of free atoms. This is a state of matter we don't see in our solar system. Our planets have water as ice, or liquid, or vapor, but not as a dissociating haze. Not in a searing sky. Detecting this required rethinking our tools. Standard spectroscopic models were built for cooler environments. They couldn't interpret the data. Scientists had to push the physics. They had to calculate how water absorbs and emits light at these insane temperatures. They had to understand the signature of a molecule coming undone. The discovery is a triumph of forensic astronomy. It proves that even our most cherished compound, the symbol of life, can exist in a form of perpetual violence. The presence of water here isn't a hopeful sign. It's a testament to extreme photochemistry. It shows that atmospheric layers aren't always neat and tidy. On Earth, the stratosphere is cold and stable. On WASP-121b, it's a dissociative inferno, a place where chemistry is driven by rupture. This turns a fundamental idea on its head. We often look for water as a marker of the familiar, a clue that a world might be like ours, but WASP 121b argues that water can be a marker of the alien. Its existence in that state tells us more about the star's fury, more than any potential for biology. It asks a question: what happens to the basic ingredients of life when the environment is too fierce? Too fierce for them to ever combine into something more complex. They are trapped in a cycle of creation and destruction, a sky that breathes but cannot nurture. If the building blocks themselves are shattered by the light, what chance does any larger structure have? This world is a boundary, a line in the sand of cosmic chemistry. It defines the outer limit, the limit where familiar substances cease to be familiar, and it makes you wonder, if water can be found in such a hostile place, what other common materials are waiting out there? Transformed by heat and light into something utterly new. It's out there in the void, a world with no address. So J318, 522, a rogue planet, an orphan of gravity. It doesn't orbit a star, it's not part of any solar system. It's just drifting in the cold between stars on a journey that could last forever. This thing formed like a star did, from a collapsing cloud of gas and dust, but it never got heavy enough to ignite. It's a failed star, really, with the mass of a giant planet, and its environment is perpetual twilight, no sunrise, no day or night from a nearby sun. The only light comes from the faint glow of the galaxy, and from the planet's own internal warmth, slowly bleeding out into space over billions of years. The climate on a world like that is written from the inside out. Without a star's overwhelming energy, the atmospheric physics are all about internal heat and convection. The planet was left searing hot from its formation, and that heat now churns the deep atmosphere, driving weather systems we can only guess at. Scientists think its skies could be layered with clouds of hot dust, even droplets of molten iron glowing a faint red in the infrared. So you have a global weather pattern powered not by sunlight, but by the planet's own cooling heart. Storms would be driven by the release of that primordial energy, swirling in a darkness so complete it's hard to imagine. The chemistry in that atmosphere would be alien, too, shaped by internal processes, not external radiation. Molecules could form and break apart in ways you wouldn't see on a star-bound world. This lonely traveler challenges what we even call a planet. Our old models say a planet has to orbit a star, so J318, 522 doesn't. It's in a category of its own, forcing astronomy to expand its language. Its discovery means there could be billions of these nomads wandering the Milky Way, dark and nearly invisible. Their existence rewrites the story of how planets form. It proves worlds can be born from the direct collapse of a gas cloud, not just from the disk around a young star, and it raises a haunting question about their fate. As its internal heat slowly fades over eons, what happens? The atmosphere itself could gradually freeze out, falling as snow of various compounds onto a surface we can't see, leaving behind a frozen, silent core, adrift in the endless night. The journey of this rogue planet makes you reconsider the bonds of a solar system. It shows a world can be complete unto itself, a solitary island of geology and weather in the cosmic ocean. And if a planet can live and die alone, what does that say about the need for a sun? What strange, internal biospheres might persist in the eternal dark, powered by chemistry and geothermal vents beneath an ice shell? The possibilities in that endless night are as vast and as chilling as the space it travels through. The idea of a ringed world, we know that. Saturn's rings, they're famous. But there's something out there that makes Saturn's look tiny. The object is called J1407b. It might be a brown dwarf, a failed star, but if it's a planet, it has something around it. Something huge. When it passes in front of its star, the light doesn't just dip, it flickers, it creates a pattern, a jagged shadow that goes on for weeks. The best way to explain that is a ring system. A ring system that's over 200 times bigger than Saturn's. That number, it's hard to grasp. If you put these rings in our solar system, they'd reach from the sun out past where Earth orbits. The size is the first thing. It doesn't make sense. Our ideas about how rings form, they come from Saturn, from gentle gravity, from small moons herding dust into bands. For rings this big, the same rules would have to work on a completely different scale. The shepherd moons wouldn't be little rocks. They'd be the size of planets themselves, like Mars orbiting inside the disk. Their gravity would have to be perfect across millions of miles. Keeping that stable is a real puzzle. One small tug from a passing star could send waves through it all, causing collisions. Or scattering the rings completely, but the data says the rings are there. They have structure, gaps, divisions. It suggests a whole environment around that world, incredibly complex. A place where moons might be forming on a massive scale, right there in the rings. This changes what rings are. They're not just decoration, they're architecture. They become the main feature, bigger than the planet itself. The dimming of the star isn't just a measurement, it's a shadow cast by these structures as they block the sun's light. J1407b, whatever it is, shows something radical. It shows that what surrounds a world can become so grand it redefines everything. The rings aren't a detail anymore. They're the story, and if a world can be defined by a halo that large, it leads to a final question. What do you call something that challenges not just physics, but what we think a planet even is? That final definition question brings us to the Kepler 51 system. There are 3 planets there. They appear to be made of cloud. Their densities are lower than anything we thought possible. They're called super puffs. Their average density is close to styrofoam, a planet the size of Jupiter but with only 1% of its mass. That's the scale of it. They aren't traditional gas giants, they're something else, vast spheres of gas and haze, held together by the faintest whisper of gravity. This is a different kind of planet. It challenges what planetary material can be. How can something that large, that diffuse, hold its shape in space? The answer might be tied to time. These worlds are cosmically young. Only about 500 million years old, a child compared to Earth's 4.5 billion. Their extreme puffiness may not be permanent. It could be a phase. A volatile adolescence. The heat from their formation is still trapped inside, raging. That internal furnace, plus intense radiation from their star, could be billowing their atmospheres outward. They are inflating, like balloons being filled too fast. Some models suggest their hazy atmospheres are actively escaping. We might be catching them in a fleeting moment. A snapshot of planetary evolution. It looks nothing like the settled worlds in older systems. Their skies are likely shrouded in high-altitude hazes. Methane or other hydrocarbons breaking apart in the light. These hazes contribute to the low density. They act like an insulator, trapping heat, maintaining the puff. This is a dynamic, evolving view of planets. It shatters the idea of a world as a static object. The Kepler 51 worlds are processes. They are events. Their existence means a planet's youth can be a period of radical change. A volatility that our static models, built on ancient systems, fail to capture. It forces us to ask if we're seeing planets in the act of becoming something else. Will these super puffs over billions of years lose their envelopes to space, leaving behind dense rocky cores, or will they stabilize, remain as permanent gossamer giants? We don't know yet, but their fleeting puff shows planets can have volatile beginnings. Their story is one of temporary extremes. To understand a world, we must ask not just what it is, but when we are seeing it. In the life of a planet, 1 billion years is just a chapter. And some chapters are written in clouds. These 20 worlds, they're more than just a collection of oddities. When you look at them together, they form this pattern across the galaxy, a pattern that seems to defy physics. You have to step back from it all, from the diamond hearts and the iron rain, and then you can see it, a profound truth. The universe isn't just a place where planets happen to be. It's a laboratory, a place for physical conditions we could never create here on Earth. Every strange environment we've found, the supersonic glass storms, the evaporating hydrogen tails, each one is a natural experiment. Conditions of extreme temperature, pressure, chemistry, states of matter we've only ever theorized. Each exoplanet is a data point, a signpost, and it points directly to the fact that our current models are incomplete. These worlds aren't exceptions to the rules. They're evidence that our rule book is still being written. This forces a kind of revolution in the sciences, but from a distance. Astronomers now, they aren't just mapping planets anymore. They're pioneering new branches of atmospheric physics for skies that absorb all light. They're writing new chapters in geology for worlds with molten rock cycles. They're developing entirely new material science to understand how diamond or titanium oxide behave inside a stellar furnace. Didier Queloz, the Nobel laureate, he noted this. The discovery of exoplanets has fundamentally changed astronomy. We've entered a new era of exploration where any single observation can challenge a core assumption. That hot Neptune that shouldn't existed challenges our theories of atmospheric survival. The cotton candy planet defies our models of how planets form. The rogue world makes us question the very definition of a planet. Collectively, they expand the envelope. They show us what's possible in nature. So this journey, it's about more than finding weird places. It's about stress testing the laws of physics themselves across the galaxy. We send these laws out into the cosmos, and the cosmos sends back answers. Answers in the form of impossible worlds, and each one asks a silent question, a profound one. What fundamental truth do we have to revise to explain this? When you synthesize all these anomalies, it leads to a final reflection, a humbling one. If our physics is just a local guide and not a universal code, what does that mean? For our understanding of everything else, for our place in a cosmos that regularly, almost casually, defies our deepest understanding, the cosmos just gave us a new curriculum. This tour of 20 worlds, it's more than a list of marvels. It's a single message. The universe is stranger, more inventive than our boldest science fiction ever imagined. Every planet we've seen, from the diamond heart to the evaporating giant, it's a direct challenge. Each discovery has stretched the fabric of known physics, pulled at the seams of our theories until they've grown. Our textbooks aren't wrong, they're just incomplete. They're works in progress being edited in real time by the data from these alien laboratories. These extreme environments aren't just curiosities. They're the most critical tests we have. Every supersonic wind on HD 189,733b, every molecule of dissociating water on WASP 121b, every silent orbit of a rogue planet, they each ask a precise, brutal question of our models. Can you explain this? And often the answer is a humbling not yet. That gap between prediction and observation, that's where true discovery lies. It forces astrophysicists to invent new mathematics, to conceive of new states of matter, to write new chapters on atmospheric chemistry. These impossible worlds are the engines of scientific revolution. They teach a lesson in cosmic humility. For centuries, we had a sample size of one. Our own solar system, we extrapolated its quiet, orderly rules across the galaxy. We assumed it was the standard model. These exoplanets have shattered that assumption. With glorious, defiant diversity, the universe is not obligated to follow our local guidelines. It plays by a deeper, more flexible set of rules we are only beginning to glimpse. Humility isn't about feeling small. It's about being open to the data, however bizarre, open to rewriting the story. So when you next look up at the night sky, that feeling is different now. It's charged with a new kind of wonder. You're not just looking at points of light, you're looking at a gallery of possibilities. Each faint star could be the sun for a world with a rock cycle, or a sky of titanium oxide, or a heart of gemstone. The greatest puzzles of reality are no longer abstract. They are embodied. They have addresses. They're waiting in the data, in the next flicker of a distant star, holding a piece of the puzzle of how the cosmos truly works.